This is the 18th example video for our course on abstract algebra. And the main lecture video was essentially about integral domains. And so most of these examples will be related to integral domains and things that are not integral domains and kind of studying some behaviors of them not being integral domains. Okay, so anyway, let's jump into the examples. So our first goal is to show that the Gaussian integers is an integral domain. Let's recall that the Gaussian integers, z adjoint I, is everything of the form a plus bi, where a and b are integers. Now, of course, you could use the fact that this is a subring of the complex numbers, and as a subring of the complex numbers, it inherits the characteristic of being an integral domain. That being said, we're going to prove it directly for practice. Okay, so let's take two elements, let's call them z and w, inside of z adjoint I, and maybe let's also assume that w is not equal to 0, where z times w is 0. So this is the setup to try to figure out if there are zero divisors at all. So if we take a product of something we know is non-zero with something else and get 0, then we should end up with z being equal to 0. That would prove that there are no zero divisors. If we find the possibility that z is equal to 0, then in fact we will have zero divisors. Okay, so anyway, let's get to it. So since we're in z adjoint I, and we know the shape of things in z adjoint I, let's maybe use that to our advantage. Let's write z as a plus bi, and we'll write w as c plus di, and let's notice that a, b, c, and d can all be taken to be integers. And now we're going to make our first little observation, and that's based off the non-zero-ness of w. So since w is non-zero, that tells us that c and d are not both equal to 0. So, because that's what it means for a complex number to be 0, the real and the imaginary part is not 0. But notice if c and d are not both 0, then that implies that c squared plus d squared is not equal to 0. And that's going to be like the important fact that we use throughout. Okay, so now let's look at our product written with z and w using these forms. So we have 0 is equal to, well, like I said, z times w, but that's a plus bi times c plus di. But now multiplying that out, keeping in mind that I squares to -1, and then gathering the real and imaginary parts, we'll see that this turns into ac minus bd. That's the real part. Again, because bi times di is negative bd. And then plus, let's see what we'll have, ad plus bc. AD plus BC times I. Now, if we want this thing to be equal to 0, it indeed means that both the real part and the imaginary part has to be equal to 0. So that gives us a nice system of equations. We have AC minus BD is equal to 0. And likewise, we have AD plus BC is equal to 0. Okay, good. And now we're going to do some manipulation on this to get to the point where we show that z is equal to 0, which proves that this is an integral domain. Okay, so what is the manipulation? Well, I want to match these first terms here. And so I'll do that by multiplying this first equation by d, and I'll multiply this second equation by c. And maybe this is known not to just zero everything out because we know c and d are both not 0. Okay, so anyway, that's going to give us acd minus bd squared equals 0 for the first equation. And for the second equation, we'll see that we have acd plus bc squared equals 0. And now we'll take these two equations and we will subtract them. So maybe the best way to see to subtract them is to take the second equation minus the first equation. But that's going to cancel the ACD term, and that's going to leave us with b times the quantity c squared plus d squared, after, of course, factoring out the b. But now check it out. From this blue square right here, we know that c squared plus d squared is non-zero. But this equation is occurring within the integers, which are a well-known integral domain. So applying the fact that the integers are an integral domain, here we get that b is equal to 0. Okay, good. So we see that b is equal to 0. But from there, we can plug this back into our original equations here, and that gives us two equations. We'll have AC is equal to 0 and AD is equal to 0. But now we can kind of play the same game. Well, first of all, we know that C and D are both not 0. So that means that, for instance, if C is not 0, then A must be 0 given this product. And if D is not 0, then that means that A has to be 0. Again, given this product and the fact that we are indeed within the integers at this stage, which is an integral domain. So anyway, both of those things together tell us that A must be equal to 0. Okay. So what we've achieved is that A is equal to 0 and B is equal to 0, but by the definition of Z up here, that tells us that in fact, yes, Z is equal to 0. But look at what we had. We had the product of Z and W is 0, where W is not 0, and that implied that Z was equal to 0, but that's exactly the condition for Z adjoin I, or the Gaussian integers, to be an integral domain. Now, moving on to the second equation, we have this ring that I'll call R, and it's made up of 4 2x2 matrices with entries in Z2. So we have the identity matrix, we have the 0 matrix, and we have this matrix here 1, 1, 1, 0, and this matrix here 0, 1, 1, 1. And what we'd like to show is that this is indeed a field. So recall, in order to be a field, well, it must be a commutative ring with 1, and every non-zero element must have a multiplicative inverse. Now, in order to be a commutative ring with 1, R with plus with addition must be an abelian group. So let's first make an addition table to make sure it's an abelian group. It's very clearly going to be abelian, but the question is do these matrices close under addition given this setup? And we'll see that they do, but we need to check that. So let's give them some names. Maybe I'll call this matrix 1, I'll call this matrix A, I'll call this matrix B, and I'll call this matrix 0. 1 because that's clearly going to be the multiplicative identity, and 0 because that's clearly going to be the additive identity. So let's see, making our addition table first, this should be pretty straightforward. We have 0A, B, 1, 0A, B, 1. So adding by 0 doesn't change anything. We already know that that is going to be the additive identity, so I'll just fill that in. Now let's perform A plus A. But that's just component-wise addition, which builds a 2 up into all of those spots. But since we're in Z2, 2 is equal to 0, so this will indeed give us 0. And there's nothing special about adding A to itself here. We could also add B to itself, and we'll see that we get 0, and 1 to itself, and we see that we get 0. Now, let's look at the rest of them. Let's look at A plus B. So what happens here? Well, the off-diagonal elements will double up. They'll give you 2 on the off-diagonal, which is 0. And then the 1s and the 0s are placed in opposite places in the diagonal entry, so that makes this add to 1. And then we're just left with A plus 1, and you can check that that is B. And now we can fill in the rest. B plus 1 will be equal to A. So let's see, B plus 1. You can see that this 1 plus 1 will zero out this off-diagonal, or this diagonal, and we'll be left with 1s in the off-diagonal, which is exactly what we wanted. And then multiplication is clearly going to be commutative, so we can fill in the rest just by 1 here. Let's see, an A goes here and then a B goes here. So the important thing is that this is closed under addition. Okay, now let's check multiplication. So it not only needs to be closed under multiplication, but we have to have an inverse for everything non-zero. And that point of an inverse for everything non-zero is important because we don't really need to multiply by 0. We'll always end up with 0. So for here, I'll just put 1, A, and B in our multiplication table. Great. And we know multiplying by the identity matrix doesn't change anything, so I can fill those in really quickly. I have 1A, B. I have 1A, B here as well. Now we've got a couple of other things to calculate, like A times A, B times B, A times B, and B times A. So let's do A times A, or A squared. So given A in the form 1, 1, 1, 0, so we've got that multiplied to itself. So let's recall the rule for matrix multiplication. We take this first row, swivel it into this first column. Notice that's going to give us 1 times 1 plus 1 times 1, but that's 2, which is 0. Then we can do the same thing over here and we'll get 1. Let's see, we'll get a 1 here and a 1 here. Let's notice that that is equal to B. That means A squared is B. And then what's A times B? Well, let's check that as well. So A times B, so that's going to be matrix 1, 1, 0, 1 times matrix 0, 1, 1, 1. Okay, cool. But now using matrix multiplication rules here, what will we have? So we'll have a 1 in the upper left diagonal, 0, 0, and then 1. So again, that's just by matrix multiplication rules, keeping in mind that we're working in Z2. That means A and B are, well, at least sided inverses. Okay, so what does that give us? That gives us a 1 here. But then I'll let you check that B times A is also 1. And furthermore, that B times B is A. And that completes the multiplication table. And we see that it's closed, it's commutative, and then furthermore, everything has an inverse, or every non-zero thing has an inverse. We didn't check 0, of course. And then you might say, well, don't you need to check some of the other stuff like maybe the distributive rules or associativity, but that's all inherited from the fact that we're inside of a matrix ring in the first place. Okay, so we've got a field with 4 elements here. That's important to know. And let's also notice that if we add anything to itself, we get 0. That's exhibited by this 0 on the diagonal. That means this field has characteristic 2. So the important takeaway here is we just found a field with 4 elements that is characteristic 2. All right, let's move on to the next example. So for our next example, we will find all units and 0 divisors in Z24. But before we do that, let's maybe talk about what's happening in general here. Okay, so the units in Zn are the equivalence classes M, so I'll just say M in Zn, such that they're relatively prime to n. So in other words, we have GCD of Mn equals 1. But we kind of are familiar with this subset of Zn already, and that is Un. So that's if and only if M is an element of Un. But UN isn't exactly equal to the ring of, or the group of units of the ring of Zn, you know, putting it in terms of our more recent notation. So that means it's, you know, fairly easy to find the units. And then what about the 0 divisors? Well, the 0 divisors are easy to find as well. And we can do that as follows. So M in Zn is a 0 divisor if and only if the GCD is not equal to 1. So in order to determine if something is a 0 divisor or a unit, we just have to find the GCD. That's all we have to do. And notice that this accounts for all elements inside of Zn except for 0. So all elements except 0 in Zn. So what does that mean? Well, there are 3 types of elements in Zn. There are units, there are 0 divisors, and then there's the number 0. Okay, so let's find all the units. So that's fairly straightforward because 24 has a nice factorization. It's 2 cubed times 3. And so its only prime divisors are 2 and 3, which means all we have to do is list all of the numbers between 1 and 24 that don't have 2 or 3 as prime factors. That's going to be a lot of primes. So let's see. In fact, that's going to be only made up of primes because the first prime squared that is not a multiple of 2 or 3 is 5 squared, which is 25. That's bigger than 24. Okay, so anyway, let's get to it. So here are the units. We'll have 1, 7, we'll have 11, 13, let's see, 14, 15, 16, we'll have 17, 18, 19, so 20, 21 are out because, well, 21 is divisible by 3, 20 is divisible by 2, 22 is out because it's even, and then 23. So we'll have those numbers. Oh, and I feel like I'm missing one, and I'm missing almost the simplest one. I'm missing the number 5. Okay, so now we've got those numbers right there. And then let's see the 0 divisors. So the 0 divisors, like I said, will just be everything else. So we'll have 2, 3, 4, no 5 because that's here. Then we'll have 6, no 7, but we'll have 8, 9, 10, 12, 14, 15, 16, 18, 20, 21, and 22. So let's count up the total. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have 15 0 divisors. We have 8 units. That makes 23 numbers in total. Then we've got the number 0, which is kind of on its own. So that gives us 24 numbers in total. So that's good to go. Now you might say, well, could we express the 0 divisorness of this or the unitness of these numbers? And we totally could, but that would include like a little bit more work. So let's look at a little of the details here. Notice that 5 inverse is equal to itself. That's because 5 squared is 25, which is 1 more than 24. 7 inverse is also itself. 11 inverse is also itself. And then let's see, 13 times 13 is 169, which is 1 more than 168, which is a multiple of 24. So actually 13 is also its own inverse. But then notice 17 is just negative 13, making it its own inverse, and so on and so forth. So I think that's pretty cool. Everything in here is its own inverse. But what about the 0 divisorness of this? Well, this is a little more exhaustive. We won't write them all down, but like notice that 2 times 12 is equal to 0. That takes care of 2 and 12. Then 3 times 8 is equal to 0. That's because 3 times 8 is 24. Let's see, 4 times 6 is equal to 0 because that's 24 again. You know, that takes care of several of them, but we've got some others as well. Notice that 9 times 8 is 72, but that's also a multiple of 24. And then you could just like play this game on and on and on to get more. That would be exhibiting the 0 divisorness of these. Okay, anyway, let's move into this next one where we show that Z7 adjoin the square root of 3 is a field. Let's recall that this is everything of the form a plus b root 3 where a and b come from Z7. So I think there's probably a trick to do this. Well, I know there's a trick if you know something about irreducible polynomials. That being said, I think at this stage, your best bet is just to do it by exhaustion. So we know that Z7 is a field. So we know that Z7 is itself a field. So that tells us that 1, 2, 3, 4, 5, and 6 are units. They're inverses. Then we just have to check everything that has a portion attached to the square root of 3. And I think you just do this a little bit at a time. And I think you can be inspired by a couple of things to guess your inverses. So let's do a sample calculation here. I'm not going to do the whole thing because it's just a lot of like multiplying things together. Let's maybe look at 1 plus the square root of 3. Let's multiply that by 1 minus the square root of 3. So my motivation there is to multiply by the radical conjugate to get me inside of Z7. So that'll end up being 1 minus 3, which is negative 2. But inside of Z7, negative 2 is 5. So what does that tell me? That tells me that 1 plus root 3 inverse is equal to 5 inverse times 1 minus root 3. That's just by like multiplying both sides of this equation by 5 inverse, if you will. But what's 5 inverse? Well, let's notice inside of Z7, 5 times 3 is 15, which is 1, which makes 5 inverse equal to 3. So that means we could really write this as 3, and then distribute it through. This is 3 minus 3 times the square root of 3. So there we found that 1 plus root 3 inverse is 3 minus 3 times root 3. But that means we've really found a pair. Notice that means that also 3 minus 3 root 3 inverse is equal to 1 plus root 3. And then you can just like continue to play this game. You could of course make like a whole multiplication table, but that's going to involve multiplying 49 elements to 49 other elements, because there are 49 elements in here. I guess you don't need to multiply by 0, so it's 40. So it's really 48 by 48. This gives us a way of like constructing them. This gives us a way to construct them a little bit more quickly. You know, that being said, I think there is some work you can do to maybe prove this is a field without finding the explicit inverses. But again, I'll just reiterate that at this stage in the game of just starting to learn about rings, I think there's nothing wrong with just doing it by exhaustion. Let's do another example. Let's take 2 plus 5 root 3. And let's multiply it by 2 minus 5 root 3. So let's see, that's going to give us 4 minus 25 times 3. So let's write that, 25 times 3. But let's see, 25 is 9 more than 14, so that makes this equal to 9. So that's really equal to 4 minus 27, because 9 times 3 is 27. Let's see, negative 27 is in fact equal to positive 1, because it's 1 more than negative 28. So this is actually 4 plus 1, which is 5. And then again, we can use the fact that 5 inverse equals 3 to write this down. So we have 2 plus 5 root 3 inverse will be equal to 5 inverse times this. Again, we get that by multiplying both sides by 5 inverse, thus getting a 1 over there. So here we have 5 inverse times 2 minus 5 root 3. Okay, and then let's see, 5 inverse is 3, so we might as well write this as 3, and then 2 plus, well, I can write that as 2 root 3 because negative 5 is the same thing as 2 within Z7. And then multiply this through, and this gives us 6 plus 6 root 3. And that being said, looking at this, I might as well write this as 3 plus 4 root 3 actually. That's because negative 3 is positive 4 inside of Z7. Okay, so that's a couple of examples of getting inverse pairs. And like I said, I think maybe now you just go at it. But I will give you a hint towards some sort of general strategy. So I think a nice general strategy would be to take a plus b root 3 times a minus b root 3, multiply those, and what you'll see is you get a squared minus 3 times b squared. But notice that's inside of Z7. And what you want to do is show that this is never 0. So show this is never 0 inside of Z7. But if it's never 0 inside of Z7, it has an inverse. Okay, but then if it has an inverse, then we can write down a plus b root 3 inverse as this thing, a squared minus 3 b squared inverse times a minus b root 3. And we in fact don't need to find the inverse because we're guaranteed to know that it exists given the fact that we know that Z7 is a field. That being said, I think maybe show this is never 0 inside of Z7 at this stage requires us to just check that by plugging plugging in all the values of A and B, which is a similar number of calculations. All right, let's move on to the next one. Okay, so two more like general questions. So the first deals with the notion of a left zero divisor and a right inverse, but this could be changed to a right zero divisor and a left inverse. So let's suppose that R is a ring with 1. It's not necessarily commutative. In fact, it's not commutative to make this interesting. Then we say that a non-zero element X is a left zero divisor if there exists a non-zero element Y such that X times Y is equal to 0. It's important that's in that order. We're multiplying on the left by X. Next, we say that an element U has a right inverse if there's an element V such that U times V is equal to 1. Okay, so our goal is to show that if U has more than one right inverse, then it is in fact a left zero divisor. Okay, so let's do that. So let's suppose that we have V1 and V2 in R, with V1 not equal to V2, such that U times V1 is equal to 1, and that's also equal to U times V2. So in other words, these are two unequal right inverses of U. Okay, but now it's fairly simple. It just uses the fact that 1 minus 1 is 0. So like I said, 0 is the same thing as 1 minus 1, which is U V1 minus U V2, which is U times V1 minus V2. But we know that U is non-zero because it has a right inverse. Nothing with a sided inverse can ever be 0. And we know V1 minus V2 is also non-zero because V1 is not equal to V2. So this condition right here is exactly what we need for U to be a left zero divisor. Okay, now let's move on to this last one. So let's suppose that R is a commutative ring with 1. Then we say X is nilpotent if there's a natural number n such that X to the n is 0. We're going to look more at nilpotence a little bit later when we talk about something which is called an ideal. Then we want to show that for any unit U in R and any nilpotent X in R, that U minus X is a unit. Okay, so let's see how this goes. So let's take, what do we want to take? We want to take n, which is a natural number, such that X to the n is equal to 0. Okay, and now let's notice that U to the n is the same thing as U to the n minus X to the n. But now we can factor that using a standard formula for factoring perfect nth powers. This is equal to, let's see, it'll be U minus X times U to the n minus 1 plus U to the n minus 2 times X plus U to the n minus 3 times X squared, building all the way up to, let's see, we'll have U X to the n minus 2 plus X to the n minus 1. Okay, so let's actually smush those all together into one thing. Maybe we'll call all of this together V. And then let's rewrite this whole thing as U to the n equals U minus X times V. But now from here what we'll do is multiply by U to the minus n. We know if U is a unit, then U to the n is a unit. So let's do that. So multiplying by U to the minus n, we get 1 is equal to U minus X times U to the minus n times V. So that relationship right there tells us that U minus X is a unit, and it in fact tells us exactly what the inverse of U minus X is. Notice U minus X inverse is equal to U to the minus n times V. And if you're worried what I really mean by U to the minus n, by U to the minus n, I mean U inverse to the n power. And since I assumed that U was a unit, that means that U inverse is like a well-defined object. And that's a good place to stop.